Hello, maybe we can you hear me? Yeah, maybe we can wait for a few minutes. Okay, so maybe we can start. Good morning, ladies and gentlemen. On behalf of the local organizing committee, it's a great pleasure for me to declare open the 28th International Conference on Supersymmetry and the Unification of Fundamental Interactions, SUSY2021, and to welcome all the participants from all over the world. This is the first time SUSY conference online in the history due to the COVID-19 pandemic and the associated travel restrictions. We have 45 plenary talks, 481 parallel talks, and more than 1,200 participants. In addition, I sincerely wish that all of you will enjoy the 5.5-day conference. Our first speaker for the opening speech is Professor Longgen Cai the director of the Institute of Theoretical Physics, Chinese Academy of Science. Longgen, maybe you can share the screen.
Okay. Can you see my PPT?
Yes. Yeah, you can see, yes, but not
Okay.
full screen. Oh, now it's okay.
Hello, good morning, everyone. My name is Longgen Cai, the director of the Institute of Theoretical Physics. We are pleased to hold the 28th International Conference on Supersymmetry and the Unification of the Fundamental Interaction, SUSY2021, in the following week. Since its inception in 1993, the SUSY conference has become one of the most important and wide-attended international meetings in high-energy physics. Due to the COVID-19 pandemic and the associated travel restriction, as you know, SUSY 2020 has to be postponed this year, and 2021 had to be held entirely online. This time, we have more than 1,100 participants, 46 planet talkers, and about 480 parallel talkers. This is the biggest one in the series of the SUSY conference. The scientific objectives of SUSY 2021 include encouraging and supporting the fruitful cross-pollination of ideas between the particle physics, cosmology, and astrophysics. We aim to provide experts in these different fields a stimulating environment for interpreting existing data and making predictions for ongoing and forthcoming experiments and observations. The 5.5-day conference will consist of both plenary and parallel sessions that will allow participants to review and discuss recent progress in theoretical, phenomenological, and experiments aspects of supersymmetrical theories and other approaches to physics beyond the standard model of particles and interactions. We do believe it will be a very exciting and successful conference with your participation and support. Take this great opportunity, I'd like to make a brief introduction to my institute. This institute was established in 1978. 1978 in the history of China was a very important year. Many important things happened in that year. Here I just mentioned two things. Due to the Cultural Revolution, the basic science research was heavily influenced. In March 1978, the National Science Conference was held. Since then, the basic science and the importance of basic science and technology was emphasized and get progressed and promoted. Another sense, the open process was initiated in this year. Our institute was established in June 1978. It was proved by the Vice Premier Deng Xiaoping. ITP has played a very important role in promoting the theoretical study, theoretical physics, and received very good reputations. Here I just mentioned some of them. ITP was the first institutions in China to award the doctorate degree. In 1984, the first postdoc program was set up in ITP. And also, ITP was one of the first two open institutions to host visiting scholars, not only for domestic one, but also the international one. 26, the first Coffee Institute in Asia, Coffee Institute for Theoretical Physics China, was set up in ITP. 2011, the Key Labs Laboratory of the Theoretical Physics was set up in ITP, which is supported by Ministry of Science and Technology of China. 2016, Penghuanwu Innovation Research Center for Theoretical Physics was set up in ITP. That was supported by National Science Research Foundation of China. The mission of ITP is to be a platform for carry out theoretical physics and interdisciplinary research, a platform for educating and fostering young talents, and a platform for domestic and international exchanges and collaborations. Professor Peng Huanwu and Zhou Guangzhao won the Chinese Military Service Medal in 1999. Peng Huanwu is the founding director of ITP, and Professor Zhou Guangzhao was the second director of ITP. Due to their great contribution to the nuclear weapon in China. In 2025, ITPC establishes the International Advice Community. Nobel laureate David Gross was appointed as the chairman of the community. There are a lot of the well-known physicists and scientists visit us. Here I just mentioned some of them. Something like the David Gross, Shelley Grashaw, Maskawa, Professor Maskawa, Professor Kipsong, Professor Friedman, and Professor Yo, etc. In 2013, ITP was evaluated by the International Experts Dynamics. The assessment is this. The ITP's mission is unique among China's physics-based institutes in that it does not have a narrow field focus, and its researchers are free to choose their problem areas. It's China's principal platform for developing the cross-field and cross-disciplinary connections that are likely to characterize many of the most important advances in 21st century science. I'm now the 18th director of ITP. My working fields is gravitation and cosmology. Currently, we have the two divisions. The division 1 focuses on the elementary particle physics, quantum field theory, gravitation and string theory, cosmology and astrophysics, mathematical physics, etc. Division 2 focuses on condensed matter physics, nonlinear science, computer physics, statistical physics, theoretical biophysics, atom, molecule, and quantum information, nuclear physics, etc. We have a lot of the academic activities, something like the curriculum, workshop, conference. We also many the seminars, including lunch seminars, and coffee time for students. We also provide many advanced courses for graduate students, something like the modern cosmology, string theory, phase transitions, and critical phenomena, introduction to molecular modeling and simulation, etc. We also have the many cooperation agreements with many research institutions around the world, something like the International School for Advanced Study of Italy and the Italy Research Institute for atomic energy and something like the APCTP in South Korea. At the moment, we have the 38 research faculty and 25 the staffs, 25 postdocs, and 159 graduate students. Most of them are PhD program. Every year, we have more than 300 persons for visit. Currently, we have the 4 teams. The team 1 focuses on particle physics, nuclear physics. This is the biggest team in ITP. The next team is gravitation, cosmology, and astrophysics. This team, we have the 5 faculty members. And another team is quantum field theory and string theory. Division 2 also have 2 teams. One is statistic physics, theoretical biophysics, condensed matter physics, atomic, molecular, and quantum information. ITP keeps open to the world, works closely with the physics around the world. ITP focuses on the most basic and key problem of theoretical physics, bring up greater talents, and aim to be an international basic research center, a base for fostering young talents, and a platform for academic cooperation and exchanges. We provide various opportunities, PhD program, academic activities, visiting programs, postdoc positions, and also faculty positions. We provide competitive salary and comfortable environments. Everybody are welcome to work at ITP. Finally, let me say again, have a very successful SUSY 2021. Thank you. Thank you for your attention.
Thank you, Runga, very much. So our next speaker for opening speech is Professor Pranas at Northeastern University, who is a member of the International Advisory Committee for the SUSY conference.
Okay, so can I share my screen?
Maybe Rungan can
Sorry.
exit.
Oh. Just a moment. I stopped my share, right?
No plan, you can share the screen.
All right, thank you. Can you see my screen?
Yeah, I can see your screen.
Okay.
But not the full screen, maybe.
It's not full screen?
It's not full.
Okay.
Yeah, it's
Is that
still not. At least from my side, not yeah.
not quite?
But maybe you can go to like yeah, it's okay. Maybe just let's do it this way.
You can see the first, right?
Yeah, we saw this. Yeah.
Okay. All right. So so let me begin. First of all, I'd like to thank Tianjun for inviting me to give these remarks. So let me begin by welcoming all the attendees to the conference, especially those who are awake at this time. And So let me give a brief history of SUSY, although the director has already mentioned this. So the SUSY started in 1993 at Northeastern University in Boston. Initially, the conference alternated between the United States and Europe. In 2000, it became global. And since then, it has traveled to Asia and Latin America. And this particular feature will continue as we go forward. Now, this is the second time SUSY conference is being held in China. The first one was in 2012. I was in that conference in 2012, so I can compare these two at this point. Compared to 2012, SUSY 2021 has a significantly larger participation, as has been mentioned already a couple of times. So that is about twice the attendance in 2012. It has nearly 5,000 abstract submissions, which is more than the total number of attendees in 2012. In fact, SUSY 2021, as was mentioned, is larger than any previous SUSY conference and has set a new benchmark for any future SUSY conference. Now, I would like to discuss the motivation for the title of this conference. The conference is called Supersymmetry and Unification of Fundamental Interactions. When I was searching for a name back in 1992, I tied these two elements together, and I like to explain why I did that. There was in the first part supersymmetry, and in the second part unification. And there is a deep connection between them. The goal of the conference, in fact, is to promote the ultimate objective of trying to understand unification. And supersymmetry turns out to be the right vehicle at this point in time, which can get us there. Currently, there is no other paradigm comparable to supersymmetry, which can take us from the electroweak scale all the way up to the Planck scale. And so that was the basic idea of putting these two ideas together in the title. Now, I would like to comment a little bit both on supersymmetry and on unification and how they fit in within the framework of this conference. Now, supersymmetry, as you well know, has many redeeming features, such as unification of gauge couplings, vacuum stability up to the Planck scale. It provides a dark matter candidate. However, I'll focus on the top one, which is the cancellation of quadratic divergence, because that has a very direct consequence for this conference. Now, as you well know, in the standard model, there is a hierarchy problem arising from the loop corrections. And the hierarchy problem is the following. For the fermions, the loop corrections are controlled. The correction is proportional to the fermion mass. So there is no problem there. For scalar masses, the correction to the masses is proportional to the cutoff. In the standard model, the natural cutoff is the Planck scale. And so this correction is very large. In supersymmetry, the quark loops cancel the quark loops, and a natural cancellation of one part in 10 to the 28 occurs. Now, this is a remarkable cancellation. Let's look back in history. What are the consequences of this cancellation? Back in the 60s, there was the problem of the strangeness changing neutral currents, where the exchange of the up quark was giving a very large contribution to K0 to mu plus mu minus. This problem was solved by the Jim mechanism by the introduction of the charm quark. and the charm quark loop canceled the up quark loop, and the cancellation was of the order of 1 part in 10 to the 9. This particular cancellation then set off the search for charm quark, which then led to the discovery of the charm. Now, let's compare that situation to the current situation in supersymmetry. The natural cancellation of 1 part in 10 to the 9 led us to the discovery of the charm quark, and now we find that there is a cancellation of 1 part in 10 to the 28 due to the same set of 2 loops. So it is therefore provides a reasonable, I would even say, a compelling argument for the observation of quarks. So the natural question is then, why haven't we seen SUSY at this point? The reason is very simple. We have not seen supersymmetry because the Higgs mass is 125 GeV, which in supersymmetry requires that the scale of the SUSY mass be few TeV, which makes it harder to observe these particles. However, this scale pertains only to the quark, not to the leptons and electroweak gauginos, which could still be light, and their early discovery is possible. In fact, the Fermilab data on G-2 recently provides a hint in that direction. The Fermilab experiment corroborates what was seen by Brookhaven, and in fact, it gets a slightly larger deviation from the standard model of 4.2 sigma. Now, in supersymmetry, one can explain this deviation by the exchange of light charginos and light S-muon neutrino loops. And these light charginos and light S-muon neutrinos are light enough to be discoverable at the Large Hadron Collider. Okay, now let me turn to the second part of the SUSY, of the title of the SUSY conference, which is unification of fundamental interactions. Now, by fundamental interactions, one does not mean only the standard model interactions, but also dark interactions arising from the hidden sector, involving dark axions, dark photons, dark fermions, and other dark entities. These dark interactions are as fundamental as the standard model interactions. Therefore, a unification of fundamental interactions should include and must include both the visible and the hidden sector interactions. In fact, the visible sector and the hidden sector are linked together in a very intrinsic way. Not only they can be linked by kinetic mixing and Stuckelberg mass mixing, but they are also linked by the fact that it is only the total entropy in the universe which is conserved. And this total entropy is the sum of the visible sector entropies and the hidden sector entropies. Similarly, the visible sector energy densities and the densities of the hidden sector enter into the Friedmann equation for the Hubble parameter. So you have h square, which involves both rho visible and rho hidden. So what is the future? In particle physics, the last decade has been dominated by the discovery of the Higgs boson, and thus we can call it the Higgs decade. Now, we hope that this decade, which is beginning this year, will be the SUSY decade. Equally important, of course, is the search for heavier Higgs, which are characteristic of supersymmetry, and data from high precision physics, which can also test new physics through the high precision experiments. We also look forward in this decade to more precise astrophysical data on inflation and dark energy and other phenomena such as gravity waves and baryon cooling and many others. For example, for inflation, a more precise determination of the ratio of the tensor to scalar power spectrum and the non-Gaussianity would be helpful in pinning down more accurately, correctly, the inflationary model. And for dark energy, a more accurate determination of the equation of state W0 at current times would allow us to check whether the lambda CDM model in fact is correct, or whether there are small deviations which may lead us to quintessence or to a phantom energy. So the scientific program of SUSY 2021 is very rich, ranging from collider physics at the Large Hadron Collider and at future colliders to cosmology. And the talks at the conference would explore physics from very short scales at colliders to physics at very large scales in cosmology. This is very much in the spirit of unification, which is in the title of the conference, which aims to tie physics at all scales. Okay, so now I would, before ending, like to thank the chair of this conference, Tianjun Li, and the local organizing committee for a very significant effort they have put in over the past 2 years in hosting this global event. And what a remarkable job they have done. Congratulations. I also like to thank the participants for their abundant submissions to the scientific program of the conference. So we look forward to an exciting meeting, and thank you for your attention. Thank you.
Thank you very much. So next, we will take pictures. And could you please turn on your video for a few minutes? So everybody just turn on the video for a few minutes. Thanks a lot. Yeah, I think everybody can turn on the videos. Okay, yeah, we have taken the pictures. Thank you all very much. Now let us start the first plenary session. Our chair is Professor Zhaoxi Zhang from the Institute of Theoretical Physics, Chinese Academy of Science.
Okay. Now we start the first plenary section. The first speaker is Yifang Wang. He will talk us the future colliders. Please. Yifang
Hello,
Wang is
everyone.
Okay.
Can you hear me?
Yes.
Can you see my slides?
Yes.
Okay, thanks very much for the invitation. So I'm going to talk about the ideas and also the plans for the future collider. So let's start with a bit of history. You can see from this plot that in the past, we have two types of colliders, the lepton colliders and the hadron colliders, and they grew up their energy following the development of technologies and also increasing over the time. Of course, over the last few tens of years, the speed has been slowed down, but I think the future colliders still is a pressing need in our field. So why we need future colliders? So first of all, we need from motivation of science. We need to answer many fundamental questions like our understanding of the space, time, universe, Big Bang, etc. And also we have a number of immediate questions like the Higgs properties, electroweak physics, QCD flavors, SUSY, actual dimension, etc. So these are all the questions in our field, and we need a future collider to answer some or even many of this or all of these questions. Of course, when we talk about future colliders, we have to evaluate each of their properties, whether this new collider can directly or indirectly related to the fundamental problems, or if this collider is a single purpose or multi-purpose, if this collider is a precision measurement or is a pure search machine. And of course, we have to look at their searching territory and their sensitivity. In many cases, our plan for the future collider has to rely quite some on the luck, and we can not always plan what we need. Of course, a future collider have to have other benefits like technology education and talent training, etc. So let's look at our pressing science questions. Of course, we all know that we have very successful standard model, but still have a lot of issues to be answered, questions to be answered. For example, if you look at the standard model like these quarks and the leptons, immediate question is what is the symmetry between the quark and leptons? Is there anything behind this picture to create this kind of pure symmetry? And also we have a well-known problem mass hierarchy, well-known problems of fine-tuning, why vacuum is not stable, and the dark matter, CP, Majorana or Dirac neutrinos, etc. So we believe that we are at a turning point and we need to answer many of these pressing questions. And a new and much deeper theory is probably needed. But of course, we have quite a number of different models. We need experiment to tell us which one is the right one and which direction is the right direction. There are many options for the future machines, and we have to answer the question, which one is the best one? Now, let's look at the best approach to design or to focus on the future colliders. Of course, you have many of these questions. Which problem, a single problem, you should look for? So I think in the most attractive, idea is to look at deviation from a standard model, which can be written like this. And we all know that at HC, we haven't seen any deviations. The direct researchers tell us that the new physics scale is at 1 TeV, and the indirect measurement with a precision of 10% tells also that the new physics scale has to be more than, say, 1 TeV. So the future machine should go, say, order of magnitude up to look for new physics at the level of 10 TeV. This requires a precision measurement at the level of 1%. And this kind of 1% also tells us that it can have a good, say, reasoning for the natureness of the Higgs mass. And indeed, a 1% kind of precision give us, say, cancellation of the Higgs mass at the level of 10 to minus 4. And so this also corresponding to a likely new physics at the scale of the 10 TeV. So we believe that 1% machine is actually valuable even for the case of not seeing a new physics. There are a lot of effort in the world right now for the future machines like European strategy update, the SNOWMAS process, the Japanese IRC process, and also there are many workshops in China talking about the future strategies of hydrogen physics. So of course, everybody knows IRC. I'm not going to repeat all the details, just emphasize that the IRC International Development Team has released a IRC preparatory laboratory proposal, and this is now in the process. So we hope that the IRC is going to be developed and being able to start construction within the next 10 years. The next linear collider option is the compact linear collider called the CLIC at CERN. And this one has a timeline established at CERN around also something like 10 years from now. This is also an expandable machine all the way up to 3 TeV, starting from initial phase of 380 GeV. CDR is ready, and the progress is still going on, and R&D is in the process. For the circular collider in China, we had a proposal to build a circular electron-positron collider around the Higgs mass, so that this is also called the Higgs factory. And this kind of machine is, since it's circular, it has 100 kilometer circumference, and the tunnel can be reused for the proton collider. So this proposal was actually initially released in the year 2012 as the first one in the world, and then now we have been moving on in the reasonably good stage. This is a CDR baseline layout. Circumference 100 kilometers, 30 megawatt beam power, upgradable to 50 megawatts, and also high Lumi, upgradable for high Lumi Z, and also for the TT bar. I'm not going through the details of the design. And similarly, at CERN, they have another machine called FCC, similar circumference, slightly different design of the machine itself, and also a quite similar, say, proton machine afterwards in the same tunnel. There are also muon colliders proposed in the world. For example, the muon collider starting from a proton driver, and then you had to have a muon cooling. Afterwards, you can have a colliding beam of mu plus and mu minus, showing in this picture. There's another approach, not using proton driver, but using a positron to generate muons, mu plus and mu minus. And in this case, you can also build a similar muon collider. So details of these machines you can find in different documents, and I'm not going through the details here. This is a summary of all the different colliders. So linear collider for the IRC, say initial phase 250 GeV, luminosity 1 times 10 to 34, cost is roughly $7 billion. The scale 2030, I guess. But I wrote it a bit earlier, let's say. And the click, again, very similar, but 380 GeV, similar cost, 2030. For the FCCEE, it's 90 to 330 GeV, 350 GeV, 8 times 10 to 34, $10 billion roughly, and 2030. And for Chinese option of the circular collider, it's 90 to 250, 510 to 34. This is because the beam power is 30 megawatts instead of 50 megawatts for the FCCE option. And the cost is half, 5 billion. And the hope for date is 2025. For the proton machine, this FCC HH, 1 times 10 to 35, $20 billion. There was a low cost, a low magnetic field option of SCC HH, 40 TV, and a similar luminosity with $10 billion for the machine plus $5 billion for the tunnel. And in this FCC HH high energy option, the tunnel is paid by the FCC EE. So this is second phase of FCC EE phase option. FCC HH low is just starting from a hadron option. So there was no electron phase before that. For the Chinese proton option, again, a very similar luminosity, $10 billion cost, and 2045 or even later. Of course, you have the electron proton collider option. For the muon collider, there were two options, proton driver option or positron option, but both have difficulty on technologies. So for the proton driver, you still have to worry about the muon cooling problem. And for the positron option, there's no enough positron beam, so there's no enough intensity, which means that you don't have enough luminosity. So these are technical issues which we need many years to work on the R&D and to solve these technical problems. Of course, we have a weak field acceleration option, but we still suffer the beam quality and the power efficiency problems. And certainly this need another, say, 20 or even more years to work on the technology issues. But of course, this doesn't mean that we cannot apply these technologies for current machines. So for example, in CPC, we are trying to use this technology as an injector, just to help a little bit on the beam acceleration. And of course, ISC and the CLIC have been also talking about this kind of approach so that we can utilize current weak field acceleration scheme, and by avoiding some of these difficult technical issues and defer them to the future. In addition to the cost, luminosity, performance, and the time scale, we also have another dimension we have to worry about, which is the technology. The new machine usually have to have new technologies. We need new technology for our own advancement. For example, superconducting technologies, SRF technologies, and we need to improve the performance of our machine and lower the cost of the machine construction. We also need to bring something new to the society, not just for us, but for the general public. So new machines should try to bring up new technologies to the society. In the past, we were successful for this WWW, for the superconducting magnets, but now for the new machine, we also have to think about this. We need to balance feasibility, cost, and aggressiveness. So currently, looking for the technologies, we do have a few realistic possibilities. The first one is high TC superconducting technologies. If we are able to develop new cables, new magnets, using new technology of superconducting cables, we may bring to the society something useful and something important. That's why in the Chinese proton collider option, we have been working right now on ion-based high TC superconducting materials. And the aim is to improve the performance ratio by almost 2 orders of magnitude and bring the cost down to the level of $3 to $5 per kiloamp per meter. And this, we believe, is feasible in the next 20 years. And we believe this should be our goal in our development of the future colliders and future technologies. Another possibility is the tabletop accelerators using laser and plasma acceleration, the so-called weak field acceleration mechanism. And indeed, we have been working on the CPC injector, hoping that we can help the development of these technologies. Of course, SRF cavities can be applicable to the quantum computing. The next one is money. We all know that we are in shortage of funding, and each of these machines is very expensive. People have been talking about that we can only afford less than 1 machine in the world because it's so expensive. But if you look at the numbers, indeed, if we're asking for a 1 machine like $10 billion, we are actually not asking for anything more than what we got in 60s as a fraction of GDP. So of course, in absolute term, each machine has been much more expensive than in 60s, but in fraction of GDP, it is not. So we should try our best to get the same kind of funding support as the fraction of GDP. And we hope that we can get the machine both in the US and in Europe. Asia now stands for 40% of the world economy. We believe that, or we hope that, we should get also 40%, something like similar funding for high-energy physics in Asia. If you look at the numbers, for example, BPC, SSC, LEP, HC, ISC, CPC, SPPC, etc., you can see that as a fraction of GDP, we are not acting much more than that in the past. So we need a global effort trying to get more support from the society. So how to get the project? Of course, we have to talk about science and the cost. So we have to improve and optimize performance cost ratio. We have to study the feasibility, including technology schedule, etc. And it is actually an international issue. So we need cooperation, but we also need competition. And lessons learned from SC and ISC is that we didn't have enough international cooperation and competition. So this is something we have to try our best. And of course, we have no science perturbations like international relationships between countries. Sometimes we need deals between countries and regions. We need public support, and also very much depend on the personality of the leaders. Of course, in the end, we need to have some luck. So, final remark about the international strategy. I believe that the highest priority for us is to get the Higgs coupling measured to a precision of 1%. To achieve this, we have different options. The first one is a circular collider, since it can give you the best precision measurement of the Higgs coupling. So FCCE and the CPC should proceed in parallel until one is approved. Competition can enhance the chance for both, and the Higgs factory is too important to miss. So in this case, at this moment, neither one can be given up. So we should move forward in parallel. For linear collider, we should try to get one of the ISC in the click, because the linear collider technology cannot be ignored, and high energy lepton colliders like up to 10 TeV will be needed in the future if new physics is discovered. So we need to continue to lobby for the ISC and continue the click R&D and the support. Only ISC and click is not enough, and because each one can only host one detector. So if the world has only ISC as a Higgs factory, we are going to have only one detector. This is not good for physics. So multi-detector is needed anyway, and we should forget about the push-pull option, because for the ISC with push-pull option, even though you have 2 detectors, but the efficiency is very low. And you waste most of your time on setting up the detector. We need to have major R&D effort for the PP collider, aiming for high TC supergalactic magnet for the future magnet, for the future collider, using say a current technology like neodymium-13 or similar low TC magnets. I believe is not a good option, and it is not sufficient technology advancement for the future. A low energy FCC HH option lacks technology impact, so it's also not a good choice. Of course, we have to maintain R&D effort for the muon collider and also for the weak field acceleration technology study. So finally, let's look at the history. In the 60s, particle physics was facing a turning point. There were a huge number of questions, and no one knows if there are answers. So pessimists lost the confidence and left the field. They missed the great discoveries afterwards. Unbelievable successful stories of GIM mechanism, quark model, CKM, electric weak theory, QCD, etc. And finally, the standard model built up our current foundation of particle physics. So today we are also facing a similar turning point. We are actually wandering around what we should do next. We probably need a theory beyond standard model, and we need a right experimental approach. So let's follow the past heroes and find a way out. Thank you.
Thank you.
Thank you.
Thanks. So now is question. Because time, maybe 2 questions. Anyone? So that means that everybody understand very well. Okay.
Yeah, there's one question.
One question there.
Hi, can I ask one question? That was a great talk. Thank you very much. And so you didn't mention about the sustainability issue very much. Do you have any comment on that?
Yes, I think sustainable issues is certainly major issues of the future colliders for both ISC, click, and also for the circular colliders. So I think the people have been working on these issues and trying to come up with some solutions. So first of all, for the linear collider and also for the circular collider, we try to improve the efficiency of the microwave system. So for example, klystrons, we try to get to the higher efficiency of klystrons, starting from current 60% to the 80% of the aim. And secondly, when we design the machine, we of course try to use all the possible technologies to reduce the power consumption. Secondly, we try to reuse some of the heat generated from the machine. So indeed, for any of these large machines, like ISC and CEP, CFCC, roughly 20–30% of the energy were wasted. It's like heat ventilate to the air. So indeed, we are working with the local industry trying to reuse some of this heat. For example, for the heat of the housing, and and also for some agricultural applications of this very low temperature heat energy. And it is not so easy to use, but very much depend where the accelerator is located. So indeed, for this reason, we hope that the machine should be located in a relatively cold area, like in the very north, in China, in Changchun, or say north of Beijing. So you can reuse some of the heat in the winter. Of course, in Japan, the ISC site is also a good place for such kind of reuse of the heating. I think many other machines have also a very similar kind of thinking at this moment.
Thank you very much.
Yeah, another question. One question.
Yes, I have one question. So you have talked about the electron-positron collider, the proton-proton collider, and the muon collider. I wanted to ask you whether you have any comments about the electron-proton collider, the EP collider.
Electron-proton collider is actually in our list. This can be an option at a later stage because you need to finish first the electron collider, and you probably have to work on the proton collider first, and then you work on the EP collider. So it is an option, and the physics are still to be studied, and also technology and the approach, how to get there is to be studied. So later stage.
Okay, thank you.
Okay, for time being, let us shift to the second speaker. The speaker is Silverstein. He will talk about the SUSY2021 and the cosmology. Yeah, let's use the title of the speaker. 25 minutes, including questions.
Got it. Thank you. Can you see the slides?
Yes.
Okay, great. Well, I would like to thank the organizers for organizing this phenomenal meeting. I'm glad to hear how massive the meeting is. So I was asked to give a kind of overview of cosmology, and I'll do my best within the 25 minutes. But of course, that can't cover everything. I'll give a brief overview with some updates that I find particularly interesting in the last year or so, and some comments of my own. In fact, I was pleasantly surprised by the invitation, the kind invitation from the organizers, because I have been a bit more on the skeptical side about the inevitability of supersymmetry compared to some of my formal colleagues. And so I'll try to explain why that is, although I appreciate very much the bottom-up arguments that were reviewed earlier today for its possibility. And I think it's a wonderful thing to test as fully as we can. Okay, I'm trying to move the slides and having some trouble. I'm not sure why that is. I'm not sure why I can't move my slides right now, so I will maybe stop the share and start over. Apologies for that. Okay, maybe I should just go with this version. Okay, at least this is moving. Sorry about that. Okay, so as we all know, observational cosmology has become a beautiful precision science. In the context of unified theory, we're particularly interested in the early universe, which is built on a foundation that's very solid from the beautiful calculations by theorists back in the 80s, which laid out concrete predictions that led to a massive observational campaign that succeeded in reproducing the structure that had been predicted by theorists. Basically, the origin of all structure in the universe boils down to a Gaussian random field that can be understood as a weakly interacting quantum field in the early universe, which comes naturally as the fluctuation, the perturbations of an inflaton field in that paradigm. So given all that, we can now do precision tests of early universe physics that are much more detailed, that probe different aspects of the physics with a good precision, a large number of modes, already 10 to the 6 modes in the CMB and more, depending on how far that goes, with large scale structure promising to increase the precision even further, which is a subject of great interest and activity these days, to see how far we can control our understanding of large scale structure to extract the information that's in principle there in the surveys of large scale structure observationally. So in terms of physics, this allows us to probe basically the wave functional, to be most general about it, the wave functional of perturbations in the early universe. And at the level of the 2-point correlation function, or the variance of the fields, that's the famous power spectrum, but it includes all ways that could deviate from Gaussianity, which could be encoded in many different ways in this functional. The prospect of measuring, constraining primordial gravitational waves through B modes proceeds with due account of foregrounds. There's cosmological information from a variety of astrophysical sources beyond that. And cosmology provides, as you all know, a probe of particle physics that is complementary to that of colliders. So it's in a good place. Let me say, just so we're all on the same page, let me say just a little bit more about the primordial perturbations. So if we parameterize the geometry in terms of a standard metric tensor of this form, we have scalar perturbations that can be fit into this function zeta, this scalar function zeta, and tensor modes gamma ij. So as I was saying, there's some wave function of those and whatever additional fields might have been there in the early universe, from which we would derive a likelihood or a probability distribution for what we do see or constrain, the scalar and tensor perturbations, integrating out the additional fields, tracing over those. And the simplest quantity to extract from this is the 2-point correlation function related to the power spectrum. But there's a lot more information in this function than that, including higher point functions and more non-perturbative aspects of it. Okay, I want to make a couple of comments here. So when it comes to the interaction of these observations with what you might call fundamental theory, meaning UV completion of what we have seen in particle physics and cosmology, such UV completions generally involve extra degrees of freedom that are too heavy to have been yet seen. And one thing that's always intrigued me is that those make a material difference in the observed phenomenology of inflation. So there are various examples of that. One of them is that if you take an inflationary model and you couple the field, the inflaton field, to other extra fields that might be quite massive, those extra fields tend to adjust in an energetically favorable way and actually flatten out the potential at large values of the field. So this underlies why in top-down string theoretic models, we see this effect, that whereas from the bottom up, you might think that the beautiful m squared phi squared model is, it's fair to say it's the simplest possible model of inflation. Once you have extra fields, heavy fields that couple in, even if they're indeed heavy, they naturally can flatten out the potential. So the kind of plateau potentials that fit the data play very well with the idea that the UV completion of our observed theory should contain additional massive matter. And in one line of development, we see that flattening effect push down on the prediction for the tensor to scalar ratio R that was already mentioned in this particular direction. In recent years, we've seen development of the theory of non-Gaussianity in new ways. So one is a kind of beautiful connection between cosmological calculations and progress in elegant characterizations of amplitudes, as well as the so-called bootstrap program, where one tries to derive general constraints from general principles. For example, asking what the impact of the unitarity of the fields in the quasi-de Sitter inflationary universe, what impact that has on the correlation functions. To me, one of the most interesting directions, which we and others have pursued, is to understand more non-perturbative aspects of this primordial distribution. So as I was already saying in its full glory, the distribution is a functional of the scalar and tensor fields. And so that allows for many possibilities. They can partly be characterized by endpoint correlation functions, but even that may not capture it. Perhaps a better way to think about this question of the non-perturbative aspects is how heavy are the tails of the distribution. And it turns out that it's very easy with multiple fields interacting for the tails of the distribution to be quite heavy compared to the Gaussian. And so rare events might be predicted. That includes potential probes within CMB and large scale structure, as well as mechanisms for primordial black hole production that are really more intrinsically non-Gaussian than the sort of traditional mechanisms involving sudden spikes in zeta at the Gaussian level. So here's a little bit more on that. In one class of examples, if you couple in as fields which live on a hyperbolic field space, which by the way connects back to ideas of supersymmetry, then you find with couplings that are simple dimension 5 interactions that you get quite a heavy tail. So we're intrigued to look into what the observable consequences of that could be. In previous work, we found that even with very heavy particles, this is another example along the theme of sensitivity to super heavy fields, one finds that interactions of the inflaton with those fields quite consistently with the overall trend of inflationary dynamics in the homogeneous universe, those interactions can produce particles, even heavy particles, in a way that's detectable. So this was work that we did with Flauger and company. It was soon understood how to what the optimal estimator for that is in CMB data in work of Munchmeyer and Smith. And recently there's been progress in large scale structure, figuring out how to make efficient computations, measurements of endpoint correlation functions in large scale structure. So I think this is a growth industry in the field, and I'm looking forward to seeing how that goes. Okay, let me move on. Okay, so just to summarize again, CMB and large scale structure measurements are proceeding. The polarization, including foregrounds, measurements thereof, and some theory of it are really continuing steadily. CMB stage 3 and 4 will be sensitive to a very important window in primordial gravitational waves, as well as other important physics. With large scale structure, recent news includes measurements in large scale structure of the cosmological parameters completely independently from CMB data. So there are two independent groups, Senatore et al. And Zaldariaga et al., who made these cosmological parameter measurements in large scale structure, landing on a value in particular of H naught that agreed with the CMB, but again, without CMB data, and with some of their data overlapping with some of the distance ladder data. In general, the idea here, as I mentioned earlier, is that large scale structure surveys collect a volume's worth of modes rather than the essentially areas worth of modes we see in the CMB with a thin shell of modes there. And there are existing efforts like BOSS. There's SphereX, which has been approved, and important proposals such as MegaMapper, which will continue this tradition and give us more and more information. And to actually extract the information of interest to test quote unquote fundamental theory is a very interesting problem in itself. And so how do we do that for traditional measurements such as non-Gaussianity of various shapes of the 3-point function? And beyond that, how do we do it for the kind of non-perturbative effects, rare events and such that I mentioned just now? So this is just a really beautiful subject that's ongoing. There are interesting effective field theory notions of how to organize the problem, attempts to use distinct properties of the primordial signal versus the way that the foreground retains a certain locality to extract the information. There's interesting uses of machine learning by for example, Seljak's group and others, Wandel's group. So this is a very active and interesting and important direction, along with, of course, the traditional CMB methods. Okay. Coming back more toward the theory. Sorry, was there a question? Okay. Coming back a bit more to the theory. One thing that's quite universal in string theory as we know it, as well as originally, of course, articulated and motivated from the bottom up, is axions. From a string theory perspective, wearing that hat now, one thing that strikes me about axions is that they really are universal. That is, it doesn't matter if what the shape of the compactification manifold internally is, or any of those choices, you always find axions. You do not always find saxions. So I would say generically, there is no such thing as a saxion, but axions are really universal. Okay, so for that reason, as well as the standard bottom-up reasons, it remains a great effort to study axion physics and test it to the best extent we can. And that has implications for dark matter, for black hole dynamics, for inflation, and so on. In a special case where you do assume low energy supersymmetry, and in the string theory context, you work with a Calabi-Yau manifold, then you get often light axions. More generally, you have an enormous number of axions, but generically they are lifted by couplings to branes and fluxes and those sorts of things that appear in string theory in the extra dimensions. So this remains a very active and important area as well, of course. Okay, getting even more theoretical, what are we dealing with in cosmology, in the biggest picture we can consider? Well, we have the observed patch that we all know and love. Just trying to get the cursor, there we are. And that is a patch of the universe in which we make these inferences from CMB and large scale structure data, with imprints from whatever primordial early universe physics led to the fluctuations that seeded all of that. But there's no reason to stop at just where our view ends, at our horizon. Beyond that is territory that surely exists. There's no reasonable theory that just stops at the end of where we see. And bringing in our best idea for quantum gravity, which is string theory, we find many different regions of the universe. And given that gravity is dynamical, we have to entertain the possibility that so is topology. And we see that in string theory, that there are topology changing transitions. So we have to ask how many components of the universe there are. So in the biggest picture we have, we're dealing with what we see and trying to understand it in the context of a much bigger picture. So this is a challenge. There is a connection between this very ambitious attempt to understand quantum gravity and observations, which has to do with the fact that I kind of alluded to earlier, that inflation is UV sensitive. It's sensitive to Planck suppressed operators. The observations are sensitive to massive fields that can appear, sensitive to the symmetry structure of the theory, the axions, and how their potentials look, and so on. And that has led us to a beautiful interaction between string theory and data, where we get some testable signatures that are still in progress. And from that, we can extract more complete effective theories. That is what we really then use to compare to data directly. So there's this beautiful interface just at the level of models that are accessible to observations. But the observations, like the observation of the cosmological constant, have led us to challenges that extend beyond the horizon that we see as well. Okay, I'm not sure how I'm doing on time, but let me say a little bit more about how this all looks in the nuts and bolts of string theory, because once we start talking about cosmology and the cosmological constant, we're dealing with gravity at a quantum level. And in string theory, we have these famous extra dimensions. In fact, the number of those can vary. There are dimension changing transitions. And if you look at how the theory in some limit descends to 4 dimensions, we can characterize the 4-dimensional potential energy, the thing that includes the inflaton potential, in other physics, by starting in some limit of the theory and some dimensionality, reducing to 4 dimensions, reducing the higher dimensional action to 4 dimensions, and including the various contributions that leads us to, contributions that come from the leading potential energy in string theory, which is this positive term. The curvature of the internal dimensions contributes to the potential energy. If you pick a Calabi-Yau manifold to insist on low energy supersymmetry, you cross out this term and you cross out that term. But one of the things that has troubled me about those assumptions is that these terms are generically there. So negatively curved extra dimensions contribute positive potential energy. And if there's, a sort of, gross way to describe what we've observed all sorts of evidence for positive potential energy in the universe, the dark energy and all the evidence for inflation, but not yet any kind of direct evidence for supersymmetry. So almost every string background does not have supersymmetry at low energies. Now, there are all sorts of possibilities, though. You can assume that or not, and include various contributions to this 4-dimensional potential, which include various defects in the theory, branes, and fluxes, which are electromagnetic fields of higher rank in higher dimensions. One thing that's important about those electromagnetic flux fields is that they take a kind of generalized form in the theory where they couple to each other and to fields that descend to axion fields, so potential fields in the extra dimensions, in a very curious way that I've written here, so that the analog of the Maxwell F² term, when you reduce it, in fact, takes the form of a flux squared that depends on axions. And that's where the axion potential energies for inflation come from. And they're very, very, very generic with a large field range that is testable with upcoming CMB data. Okay, so the 4D potential has those terms I mentioned, but it also has an important contribution from what we call the warp factor. So the metric contains extra dimensions with some geometry or beyond. Sometimes it's more abstract even than a geometry. And the 4-dimensional component of the metric is multiplied by a warp factor, a redshift factor, whose equation of motion is a constraint. And when you impose that constraint, as you should in GR, you get an equation, which is actually a nice linear equation in 4 dimensions, which is like a Schrodinger problem. And when you plug back in the solution to that equation, you get a potential energy which depends on the solution for this warp factor in a way that's very, very physically important and interesting. So you see it here, it redshifts away negative energy sources that get too strong, helping to stabilize the theory. That's more or less the effect it has, in addition to a gradient contribution that, combined with the original internal curvature contribution, makes for a net curvature potential energy in 4 dimensions. Okay, so with all that, there's a kind of litany of de Sitter mechanisms in string theory, and they can kind of be classified in terms of power law stabilization with a high scale of supersymmetry breaking, or non-perturbative stabilization with a sub KK level of supersymmetry breaking. One of the new developments is sorry, could you say that again?
3 minutes.
3 minutes. Okay, thank you. One of the new developments this year is a new mechanism, which is particularly simple in terms of its list of ingredients, which involves taking seriously the generic negative curvature induced positive potential energy that we get in string theory or M theory, including the Casimir energy that is automatically generated at the quantum level and the flux that I mentioned earlier. This mechanism I find quite interesting because the hyperbolic geometry that appears internally is not just kind of motivated by genericity, but it has a famous mathematical property called Mostout rigidity, which, along with the effects of the warp factor that I just summarized, contributes strongly stabilizing effects. So the three contributions that I mentioned earlier, the curvature, the Casimir energy, and the flux, give the correct shape and tunability to stabilize the overall volume of the space. And then other directions are strongly supported by this mathematical rigidity property. This being a kind of summary talk, I'm not going to go on about this more than what I've just said. But if you're interested in talks on it, as opposed to the paper, which is also available, you can find numerous examples this summer if you're interested. Okay, so the summary of that part of my talk is that the potential energy in string theory is mostly positive, has negative sources that are needed to produce metastable cosmological terms. It's generically not supersymmetric. So if we see supersymmetry, that'll be a very interesting special case. It typically has axions. It typically has, those typically have large field range inflationary potentials, but inflation can work in many ways, and that includes other examples with smaller tensor to scalar ratio. So I've already said this, but since I have the opportunity, I do want to stress this fact that although supersymmetry is a beautiful idea to test, it should not be confused with something that is dictated on high by string theory. For this reason, that almost all the configurations, solutions in string theory do not have that property. That doesn't mean it's wrong for nature. It might be right for nature, but it's to me, it makes the whole question a lot more interesting because of this this kind of tension. Now, of course, all physics that has been done, just all of it, the standard models of particle physics and cosmology, all of condensed matter physics, gravitational physics, et cetera, does not require supersymmetry for the theoretical control and understanding that we have of physics. And the same methods, the same methodology we can use, and we do use in the context of string theory. The way supersymmetry has mostly been used, been needed in string theory has to do with extrapolating from weak coupling to strong coupling, which is a beautiful story in itself. But for modeling nature, modeling early universe cosmology or particle physics, we don't actually use that. We are working in a perturbative regime often, and we can use perturbation theory, numerics, mathematical theorems, such as those I've already quoted, and a number of other handles that we have on the theory to maintain control even without supersymmetry. So I think we should be clear on the logic of that while still exploring all these possibilities rigorously. Last thing I should say is that when it comes to this connection between string theory and cosmology, it's not all or nothing. So there's this intermediate where the connection that we have between theory and experiment is real, but it is model and wave function dependent. And just the discovery of the cosmological constant has given us a lot to think about. We need a framework for quantum gravity consistent with the observed cosmological constant, and that's something that many of us focus on as well. So here's a brief summary of some developments there, which I won't have time to explain, but there's a beautiful discovery in theoretical physics that gives a formula for energy levels that matches perfectly with those in de Sitter space. And that's kind of my favorite approach these days. Euclidean quantum gravity has had a resurgence as it has provided a famous calculation of the famous Page curve in black hole physics. And there are some other directions that are also quite interesting. So this remains an important area as well. I was going to give a technological spin-off of theory, but there is not time for that. But if anybody's interested, you can ask more about this. Instead, let me go to my concluding slide, which is a bunch of questions that perhaps characterize the state of the field and the near future that we can pursue. So thank you very much.
Thank you. Thanks a lot. So now it's question time. Maybe there are any questions? It's no. Really? So thanks again for Sylvia's turn. Thank you, thank you. So, oh, there is a question. Please.
Oh, yeah. You said that the saxion corresponding to the axion would have to have a Kaluza-Klein mass. What happens to the axino? Is there an axino, or does that go away as well?
Yeah, all I'm saying is that given that the supersymmetry is broken, let's say at the KK scale, let's say we do a compactification on this is from the string theory perspective. If we do a compactification, say on a hyperbolic space, then the supersymmetry is broken. The axion survives because it's it's a gauge field, it's a potential term, and it survives in the usual way. The fermions are lifted. So hyperbolic manifolds are generally very rich and rigid as you go up in dimension, but for sake of this discussion, we could talk about a Riemann surface, which everybody is familiar with. And there, that the circles in the Riemann surface are what we call Schirk-Schwarz circles. They as you go around, if you have a two-handled donut and you go around the circle in the middle, that's a Schirk-Schwarz circle. It can smoothly contract off. And so that breaks the supersymmetry at the KK scale. So yes, the fermion partner is lifted. There's no such thing as a saxion, but there is the axion, and the axions proliferate in these, especially in these non-supersymmetric limits of the theory, which I find quite curious. In any case, they exist in both cases, which was my main point.
So you say the axino also goes to the KK scale?
Yeah.
Okay, thank you.
Yeah, thanks. Thanks for the question.
Okay, no more questions. So thanks. Let us shift to the next speaker. Morton Ito, talking about a theoretical overview of the muon G-2, please.
Yep. Thank you.
25 minutes.
Yes. Sorry. Okay. So thank you very much. And today I'm talking about the muon G-2. And actually the second speaker is the speaker of the Fermi level experiment. So here I'm focused on the theoretical side of the muon G-2. So today I talk about the two parts. The first one is the standard model part, and the second one is the new physics interpretation. Okay, so let me start. What is a magnetic moment? The G factor. The magnetic moment is, as you know, it's an interaction, magnetic interaction with a spin, whose Hamiltonian is given right here. And here mu is a magnetic moment, which is proportional to spin, the muon spin. and there is a G factor, G is here, and that is unknown, and that is predicted by the Dirac equation. So this is a Tweedy level Lagrangian, and from the Dirac equation, this interaction term in the non-relativistic limit will obtain G equal exactly 2. But this is at the tree level, and by including the radiative correction, so this G is deviated from 2. So this deviation is, as you know, it's called the anomalous magnetic moment, or simply say it's G minus 2. And this G minus 2 is divided by, as normalized by 2 and denoted by A. So this is today's target. And I think that the next speaker will explain in detail, but let me show only the results here. So the Fermi-Lab published a first result based on the data set of the round 1 experiment, whose data set is as large as BNL, which is a previous experiment, previous measurement of the muon G minus 2. And the result is here. It's very precise. And they confirmed the previous BNL result, which is here. And by combining these two results, we obtain here. So by taking the difference from this experimental result from the standard model value, we obtain non-zero result. And this difference is now 4.2 sigma level. So it's exciting. So this is a status of the experiment. So BNL result is here. That is the previous result, and the new result is here. And these are consistent to each other. And by combining them, the experimental value is here, and the standard model value is here. So there is a 4 sigma difference. So this might be a sign of new physics. So today's talk is about the two parts. So the current status of the standard model prediction, and the second part is a new physics interpretation. Particularly paying attention, I'm talking about the supersymmetric models. So let me start from the first part. The standard model prediction is now the standard model value. There is a new consensus value of the standard model value. That is published in the white paper, so-called the white paper, which was published in the last year. And there are 4 contributions to the standard model. The first one is a QED, and the second one is an electric contribution, and the third and fourth one, the hadronic contribution. But depending on the structure of the hadronic contribution, there are 2 types of contribution. First one is a hadronic vacuum polarization, and the second one is a so-called hadronic light by light contribution. And of course, the QED is dominant, but it's already very precise. And the electric contribution is the smallest, but it's also determined pretty well. So the problem is the hadronic vacuum polarization. Actually, there is after the white paper, the new issue has been raised. There is a discrepancy between the white paper value and the new latest result. So let me explain this issue. So traditionally, as in the white paper, the hadronic vacuum polarization has been determined by using the hadronic cross-section. Actually, this is a diagram of the hadronic vacuum polarization, and this is unknown. And we want to determine this part. And this part is fortunately related to the cross-section with E plus E minus 2 hadron by using the gauge symmetry, analyticity, and unitarity. So it's very direct. Actually, you obtain this result. So the left-hand side is here. The right-hand side includes the R ratio, which is proportional to the cross-section of the E plus E minus 2 hadron, and determined by the experimental data. And Ks is so-called the kernel function, and that is a very simple analytic known function. So once we measure the R ratio, then we can determine this hadronic vacuum polarization. So this is a traditional approach and so-called the R ratio approach. But this hadronic polarization can also be determined by using the lattice from the first principle. So it's completely independent of the traditional approach, a ratio approach, and very recently, yeah, it's also published in the last year, but accepted by this year. So the BMW collaboration published a new result, and their result is here. And this blue band shows that it's Fermi level plus Brookhaven result. So it's the new result, the new BMW result is consistent with the experimental Fermi level G-2 result. Of course, this is deviated from the white paper value, which is indicated by this R ratio. So the difference between the BMW and the R ratio is currently about 2 sigma. And this deviation has not been understood yet. So as for the lattice, we have to check this BMW by independent groups. So such analysis are now ongoing. And another possibility is, of course, there are some deficits in R ratio measurement. But the R ratio is also used in other observables, such as electric pressure observable. Actually, electric pressure observable can restrict such a deficit. Actually, the R ratio affects the electric observable by the running fine structure constant. So it's completely non-trivial to reconcile these two electric pressure and the R hadron measurement and this BMW result. It's completely non-trivial. And I think that this kind of topics will be given by short talk by Anders Kribeling, maybe today. So if you are interested in these topics, so please listen to this talk. So anyway, this is the status of the tensions. So this is a new result of the Fermi level. And that is deviated from the standard model value based on the white paper, I mean, that's the R ratio approach. The difference is currently 4.2 sigma. But instead of the R ratio approach, if we use the BMW lattice result for the hadronic vacuum polarization, there is no difference between the Fermi level result and this result. Instead, there is a 2.1 sigma level difference between these two results. So there are tensions, and we don't know the reasons. So we have to check. So the red characters are the future prospect. The experimental side, the Fermi lab is still ongoing. They already finished up to the round 4, I guess. And the next year, the round 5. So aiming at reducing their experimental uncertainty by the 4. And another experiment by using a completely independent approach technique is ongoing. The JPAC experiment, that is the JPAC experiment is planned and still on it's planning. And also as for the R ratio analysis, the belts, so they are based on the experimental data, and their experimental data in the near future updated by BEL2, BES3, SHMD3, and so on. And also the mu-E is proposed, that is the experiment to measure E minus mu plus scattering. So this is another independent approach to determine the hadronic vacuum polarization by using the experimental data, of course. And for the lattice side, the several lattice analyses are ongoing. So this will be checked in the near future. So there are tensions, and all the tension can be checked in the near future. So this is the status of the standard model side. And in the next 10 minutes, I will explain the new physics interpretation. Of course, there is an issue. There is an issue about the standard model prediction. It's interesting to talk about, consider the new physics interpretation. So this is the status of the difference. So if we choose a white paper value, there is a 4 sigma deviations. And interestingly, so I didn't say, but this is of order 10 to minus 9. And this deviation is larger than the electric contribution, which is here. So the difference is larger than the electric contribution. That means that we naively expect the new physics in electric scale, but we haven't discovered such new physics in electric scale. So we need some enhancement mechanism we need some special mechanism to enhance new physics contribution to the muon G minus 2. So there are two possibilities. The first one is assuming the right particle, and another one is a new particle is heavy, but there is some enhancement mechanism. Actually, there are many models has been proposed. This is the representative form of the new physics contribution to the muon G minus 2. It's proportional to the new coupling squared divided by the roof factor, and the mass appears in squared right here. So one of the easiest way to enhance this contribution is to consider the right particle. Instead, in order to avoid the experimental constraint, we should consider this coupling is tiny. And such models has been proposed, provided by the, say, 2 Higgs doublet model, the U1 mu minus tau model, accelerated particle model, and so on. And as for the heavy particle, then we need to enhance this contribution. Actually, there are several models. There are many models. The supersymmetric model is categorized in this here, and Reptgok model and vector-like fermion model. So there are specific enhancement mechanisms, and in many of them includes enhancement of the chirality flip. Actually, as you see, the magnetic dipole operator has fermion with opposite chirality. So if the chirality flip is enhanced, then this contribution can be enhanced. And these models include such enhancement mechanism. And these models are also discussed with other anomalies such as B anomaly and dark matter and so on, and also relationship with the GATT model, grand unification, is also discussed. So if you are interested in these models, please visit the short talks by these guys. But anyway, so I want to say that almost half of the talks discuss about the supersymmetry. So SUSY is one of the major targets. So let me focus on supersymmetric model so far from now on. Okay. The essence of the SUSY interpretation is very simple. It's given one loop, and in the one loop diagram, the muon, muon's neutrino, and changino appears. And this is a very rough representation expression of the SUSY contribution to the muon G minus 2. And so you can see there is a tangent beta factor, which is as large as order 10. And this essentially comes from the chirality flip. Actually, the muon-Yukawa coupling in SUSY model is given by is enhanced compared to the standard model Yukawa coupling by tangent beta. So this is essentially the source of this tangent beta. So chirality flip is naturally enhanced. Chirality flip is naturally enhanced in supersymmetric models. Actually, there are three types of the contribution in SUSY. The first one is the right Wien-Higgs scenario, and the second one is the right Wien-Higgs scenario, and the third one is the pure Wien scenario. And so let me talk about the right Wien-Higgs scenario, because this is usually largest contribution. In the right Wien-Higgs scenario, whose diagram is given by here, the supersymmetric particles are the muons, neutrino, Wien and Higgsino. So these particles are assumed to be right to explain the muon G minus 2 discrepancy. And we also assume that the Bino as lightest SUSY particle. And yeah, of course, tangent beta is assumed to be large, which is fixed to be 40 in this analysis. And these orange and yellow regions are favored by the current discrepancy of the muon G minus 2. And as you see, the SUSY particles, the charging mass and the muon mass should be exist in about 100 to 1 TeV. So this is a target of the LHC experiment. The LHC search can be divided in two categories, depending on the mass spectra. When the lepton is relatively light, such a region is here, and when the electroichino is neutrino or chargino, so electroichinos are light, that corresponds to the green region. So for the light lepton region, so the leptons are light. There are many leptons in the final state in the LHC experiment. So by searching for multi-lepton channels, the constraint is already very severe, and almost all parameter regions are also already being excluded. On the other hand, in the right electroichino regions, the standard model bosons are light, so these particles are produced in the final state in the LHC experiment. And as you see, the very wide parameter region is still allowed. Actually, you may wonder why it is so weak. Actually, in our setup, in the previous setup, we assume to be the Wien mass is about half of the Wien mass, which is called the gut relation, which is often called the gut relation. In that parameter region, which corresponds to the here. So this is a plot of the exclusion.
3 minutes.
Yes, thank you. So this is a plot of the excluded region, and the yellow region is covered by the WZ production channels, and blue region is covered by W and Higgs boson final state. So this parameter region seems to be covered by W and Z, and the mass is about 500. So this 500 seems to cover almost all the parameter region, but it's not true, because in this analysis, the experimental analysis assumes that the branching ratio producing W boson and Z boson is assumed to be 1, but it's not realistic. Actually, in our setup, this is a branching ratio of the neutralino decay. So neutralino mainly decay into Higgs boson instead of the Z boson, because in SUSY models, there are no Wien-Z interaction. So this is not realistic. So we need, in order to study the muon G minus 2 parameter region in realistic setup, we need WH. I mean, that the blue region should be extended to this side. And so what happens if we consider the BNO, this relation doesn't hold, but the situation is not so much changed because the branching relation is cannot be close to unity anyway. So the conclusion is very simple. Oh, sorry, very simple. This parameter relation is widely allowed. And I don't have much time, so let me go very quickly to explain about the pure BNO scenario. It's very special. Actually, in this parameter region, the chirality flip is enhanced not only by tangent beta, but also by mu parameter. Mu parameter is a Higgs mass parameter. And actually, in this plot, the mu is maximized. And it's interesting to see that I say that the tangent beta is favored to be large in the previous case, but in the current case, the smaller tangent beta with extremely large mu parameter is favored. As you see, if we take tangent beta is 50, the mu g minus 2 parameter region is very narrow. But if we consider the tangent beta is 5, but with large mu parameter, then the mu g minus parameter is wider. This is because the constructive contribution to mu g minus can be suppressed if we consider the larger mu parameter. And the blue region is the LHC constraint. So this parameter region is allowed. Of course, this is very narrow. And the mu mass and the neutral mass is degenerate. So it looks artificial, but from the viewpoint of the dark matter, it's natural. Actually, in order to explain the thermal abundance, the star quadrilation is one of the famous scenarios. In that scenario, this degeneracy, the degeneracy between lepton and the neutralino is naturally realized. So if we consider the dark matter as well as the mu g minus 2, this is in this plot, both are explained. So, and there is a parameter, the mu g minus parameter region is here. And it's interesting to say that the white parameter region can be covered, can be checked by near future dark matter direct detection experiment, such as Xenon 14 and Panda experiment. So this is summary. The Fermi lab confirmed the mu g minus 2 discrepancy at the 4.2 sigma level, and white paper has been now published. But a new issue was raised about the hadronic vacuum polarization. And if the discrepancy is confirmed, it's a sign of new physics, and there are many new physics proposed. And so if you are interested in those models, so please visit the short talks, and the SUSY is a major target, and such scenario can be checked in the near future. So thank you very much.
Thank you very much, Indo. So that's the question. Is any questions? Because of the time, we maybe one question or two.
Sorry.
And also the question can ask for in next speak after, because the next is about the experiment.
Yes.
Yeah. So maybe save time. The questions time for both of the talks. Okay. So now let's shift to the next speak about the first result of Fermi Lab mu g minus 2 by Dr. Lee.
Hello, can you see my slides?
Okay, yes.
All right, okay, thank you. So thanks a lot for the invitation. I'm happy to give you the first results of the
25 minutes in principle, but we the time is spent a lot.
Okay, that's fine. I will try to go through this, in a short version. I'm assuming some of you already see this, from the press release and other conferences. So okay, so let's go ahead. So this is a MUON-GMAS2. We have like 7 countries and about 190 collaborators, and this is my institute. Okay, a brief motivation why we are interested in GMAS2. We have a prediction of G equal to 2, but as experiment, we always interested to see what is a natural world tell us, and that's actually done almost like 60 years ago. This slightly different from the theory prediction. So that's the theme of the GMAS2 experiment. We always get quite close to theory, but not exactly. And that's the power of precision measurement. So where this 0.1% deviation come from is it come from empty space. As it turned out, the space is never empty. There's virtual particles and presents in the vacuum. So that's why we have all these corrections to it, which is already actually covered by the previous talk. So I will not go to the details of all the theory. So let's just steal one slide from the theory initiative. We published one last year, and there's a QED correction, weak correction, hadronic vacuum polarization correction, and light by light corrections. And it's just amazing to see that how accurately these calculations can be calculated. You see, this QED calculations, even though it has the largest contribution, but the precision is, enormously small. It's like 0.001 ppm, right? Almost PPB level. And the largest one is, of course, from the HVP, which we already discussed by the previous speaker. But let me just briefly go through them anyway. From the muon experiment point of view, we also try to improve it over the last 50 years. So this is what at the beginning at the Columbia, and then moved to CERN, and then to the BNL, and then finally to the Fermilab. You can see how rapidly the errors decrease over the years, and this is a table before our recent announcement. So before the current announcement, we have like 0.4 ppm, and then the new one, is very excited. This is even before that. It's already like nearly 5,000 citations. Now I'm pretty sure I didn't update this citations, but I'm pretty sure it's over 5,000 now. And then the new results will get more citations starting from this year. So even though this is already discussed, but let me try to recap the summary anyway. So this is before this year's new measurement. You see there's a big gap between the theory and experiment. And then this is from the theory initiative. This is again from the experiment. And then there are various different, all these kinds of, calculations. So there's an enormous amount of interest and effort put to that. So we all should appreciate the theory friends for doing that. And these are the, the ones used in the recent white paper, 3 most precise ones. And then this is somehow like a zoomed in picture, right? This rings, and then there's a big discrepancy between the theory and experiment. And this is the one that's already discovered, talked about by the previous speaker. but just want to reiterate, like from our experiment point of view, we don't pick and choose which series value to compare, right? We're just waiting for the series community consensus for the value to compare. And this is what I heard from our series friends, the recent latest results by BMW, with, small error here, right? There's still a need for the study compared to the, previous status calculation, which has a large error, it's, needs to be further studied. Okay, all right, so let's go to the new comparison. So this is again, new results, just shown. And then just want to emphasize that this one has a big discrepancy between theory and experiment. So there's a strong evidence for beyond standard model physics. And, especially, since we're in this SUSY conference, there's many new physics can expand this. But, I, limited by time and also by, different areas, it's better for you to refer to our theory talk. So let's go to the experiment side then. So how it can be measured so precisely, I got asked many times by different experiment friends and also theory friends. So let me try to give my personal interpretation of this. First, this is based on a solid experiment principle. As I said in the previous slide, there's like over 50 years of development, right? So it will be very, very surprising that somebody would find a flaw in this all these years of established experiment. So tested and improved over half a century, and we have huge statistics, right? So we have like 10 to the 20th proton on target, and then you get these amount of muons, and then you select 10 to the 11th of the positrons. So this is very precise, from large sample statistics. And then we have a highly uniform and stable magnetic field, which I explained in the future slides. And it has like sub ppm level uniformity. So this is amazing. And then we have precise beam monitoring. We actually use a tracker, right, to extrapolate and monitor this beam motion. Because we actually have coherent betatron oscillation, it's highly reduced and then monitored by our experiment, which I will also explain in the future slides. And then finally, the background is nearly free. There's still some background, but it's highly suppressed, right? There is some lost muon, which means a muon which does not decay, it just hits our detector or it spin out of the, containment, but it's largely reduced. And also there's a pile-up effect, which means you have two or more positrons hitting the same detector area within a short amount of time. And this is, somehow irreducible, but still we mostly understood its effects and correct for it. Okay, and in the future slides, I will explain all these points briefly because of the time. So first, the experimental principle. This is a brief overview. You have protons, you get pions, and then decays to muons, and then you get an inflector. You inject into a story ring, and then you have kicker and the quartz to make everything stable within this ideal orbit. Okay, and then because of the CP violation, you have highly polarized muon. This is like a foundation of the experiment. And then, as I said before, this A is defined as a deviation between G and a 2. And then because this muon will actually precess within a magnetic field, and then you get this frequency. And then because of the polarization of the muon decay, you actually get the muon spin direction from the decayed electrons or the positrons. Actually for this experiment, we mostly actually deal with positrons, but we have the possibility to do electrons as well. And then you take the difference between these two frequency, between the precession frequency and cyclic sound frequency, and then naturally you get your omega A, which is G minus 2 divided by 2 A mu. So that's the experimental principle. Okay, and then the rest is actually classical electrodynamics, right? This mostly theory background has been laid out, almost 60, 70 years ago. It has been calculated very rigorously. For example, I only talked about the first order calculation, but the muons actually, make a horizontal movement, circular movement. But what about the molecular movement? You would have to use the electrostatic quadruples to confine muons vertically as well. But once you have that, classical electrodynamics, it dictates that you have to write more terms, right? You cannot just write a simple first order terms anymore. So then you have to expand this. I just pick, this equation, from the previous literatures. You can see that you already immediately have this term and then this term, right? And then it's challenging to experiment to measure all these, right? We can do this easily, but all these are difficult. For example, you have beta there. Okay, you have to calculate the speed of it, and that's very challenging. So how to measure this is nearly impossible, seems like. But fortunately, we can actually control the coefficient of this term, the third term. You can actually choose a specific gamma. So that's where we see magic momentum. And then this one is largely canceled. Of course, this is only minimized. You can never get this so exactly zero, right? So there's some residual electric field correction, but that we can handle, right? So we can always do that to, get the correction. And then additional complication comes in when we have the coherent beta channel oscillation. What is this coherent beta vision anyway? This is like a muon beam will actually swim and breeze. So actually we'll do a little wiggle, and then actually the width of this thing will also breeze. So this is like 3D dimension change of the muon motion. So, and then it goes directly in both directions, vertically and horizontally. So this one, this presence of this CBO, and then also because of this electric field and then the magnetic field, this will introduce the pitch correction and high order corrections. So these are what we call the electric field and pitch correction, and these are what we call the high order corrections. So these all have to be taken care of before we do the final measurement. And again, just to give you an idea, what is this CBU, why it's so important, and this is real. This is not some imaginative effect. This is a real physics effect. So this is a muon going through. If it doesn't do any CBU, it will go straight line, right? But actually it doesn't. It has this wiggle there. And then if you look at on the right, you can see that how this thing moves, right? This is radial position. This is the vertical position. You can see that actually moves in both directions. So there's the breathing effects and additional radial and vertical frequency. And this can also be seen by our beam monitoring scheme. As I said, we actually have precise beam monitoring thanks to the tracker. We can actually extrapolate the beam where the muon goes. And you can see this is again the radial position. And then you can actually get its mean value and then its sigma. So you can actually get some frequency from it, right? And that's how we can model it. Okay, so this is the CBU. Once you have that ready, and then you can go ahead correct for the residual electric field correction. So this is a general formula, which I will explain later. But for now, you just see this is our correction factor, CE. So this is the thing we're interested in. And this coming from this term, which I explained in previous slides. And then this is the beta dot E term there. Even though this one is largely suppressed, there is some still residual effects there. And this is again from this 2D distribution plot. You can see this is XE is the X position of the positrons, right? So if again, in this 1D plot, then if you go to this side on the right side, then you can see this is high momentum. If you go to the left side, this is a low momentum, because this on the left side, there's a ring center, and the left side on the right side is the up side of the ring. So it's natural to say that this thing will go to higher momentum when you move to the right. And it's also interesting to see that this beam actually is not perfectly symmetric. You can see it's actually tilted straightly outside. So this is because due to the beam tuning effects and beam dynamics effects. So we can actually all model this from our data. You can see this is different sets of data, right? So from that, you can actually get the CE in this equation. I will not explain the detailed derivations. You can look at this paper to get some ideas. But the basic idea is the CE actually depends on the x position distribution, the average x squared distribution of the positrons. So that you get that, and then you can get the corrections. You can see this correction effect is actually quite big. It's like 0.45 ppm. But the good thing is, we were able to model it, fairly precisely, and the uncertainty is only 50 ppb. So this is electric field correction. And then let me move quickly to the precision field measurement. So I said it's highly precision field. So let me explain why it's highly precisely measured, because we have many probes, right? So this is actually our vacuum chamber, and this is from the fixed probe, and then inside you can see there is a small device. This is what we call trolley, and this is where the beams go to, the muons go to. Of course, when beam is off, we can use this trolley to go through the same path that muon goes to, and then to measure the field that muon sees. So that's what we call the trolley the trolley probes. Right?
3 minutes.
All right, thank you. Let me try to hurry this up. So there's use a free induction decay to get the muon field corrections, and then you monitor it to get the feedback. Okay, so after all this device, and then you can see how precisely you get. So this is azimuthal directions, and then you can see from before the shimming, how we make it uniform. You can see there's large deviation, and after the shimming technique, this thing gets very precisely. And then this is from compare with BNL, we actually get 3 times smaller than uniformity than BNL. Okay, and then let me quickly go through the omega A part. So omega A part is the precession frequency. We use the basic principle that when the spin and the momentum aligned, when the when the positron's electron spin and momentum aligned, then you have a boost along that direction, so that you have a high energetic positrons. When they are anti-aligned, then you have a reduced momentum. So, and then this modulation is the precession frequency we are looking for. So this is a simplified version of that. Okay, this is supposed to be a cartoon, but okay, that's fine. I don't have time for that. So let me just go to the left side. You will see this wiggle plot. This is a 2D. You have time and energy. And then you will see this wiggle there, but then you will see all these things. This looks weird. This is actually the lost muon background I mentioned previously. And this is the muon which did not decay, right? Directly hit the detector. But then immediately you can see you can make a cut, right? You can make a cut. So for example, here, you can get rid of all this, right? So that's why I said it can be highly suppressed. So after you do all this, and you can see this wiggle plot beautifully, and this is the round 1 data we have. Okay, so then let me put this together for the omega A. This is this ideal and naive case of the 5 parameters, but actually, in a realistic case, there's many more corrections, right? The pi of correction I mentioned early, I didn't have time to explain this gain corrections. And then I explained this CPU and then loss muon. I explained this also. So you add all these into your fitting parameters, which is explained in this paper. And then you can see that if you have a raw 5 parameters, you can see there's a large residual, right? So this is a fitting and this is a residual, which is data minus the fitting function. And then you have all these corrections, 22 parameters, you see the residuals are largely reduced. So which means you have very good fitting. You can see the chi-square is very small, almost equal to 1. And then, okay, I don't have time for this. This is FFT. This is just to show that you have different, spectrum, right? After corrections, right? You don't see it anymore, right? You only have a 1 residual term there. Okay, and this is a muon average field, which is a muon, which is the field seen by the muon. Okay, I don't have time. I'll skip this. So let me explain the final measurement. So the A mu is actually measured by the omega A divided by the omega P, and then plus a bunch of constants, which measured by other experiments very precisely. And then explained by this general equation. So this is the omega A I have introduced before, and this is the field. And then this is the average field, average muon distribution. And then you combine all this together, you get our final results. This is systematics. Again, I don't have time to explain this, but you can feel free to look at this. This denominator and numerator, all these kind of systematics, right? This has been all taken care of. And then this final results is what we shown before. And then you can see that this is a still statistically dominated analysis, right? The systematics actually is fairly small compared with the statistics we have. So we have actually largely statistics dominated. We have 50% smaller error than the BNL, and there is a good agreement between these 2 experiments. That's why when you combine them, you have increased significance. Okay, finally, maybe just 1 minute to explain if it is not new physics, what else can it be? From experiment point of view, could it be from statistics from creation? It's actually highly unlikely because of the high significance. It's 1 out of 40,000, 400,000 chances. And could it be experiment bias? It's for the measurement itself, I always say it's unlikely, because of the history and also many consistent checks we have. For the experimental bias, it's possible, right? But also, not very likely because of the systematics checks we have done, right? But of course, the final cross check will have to be done by a totally different experiment, which is J-Park GMAS2. And then the human bias is also unlikely due to the double blinded analysis, which I don't have time to explain, but you have to trust me then. And then of course there's theory calculation error, which briefly explained by the previous speaker, and then also maybe also by other theory friends. There's going to be some consistent check between traditional and lattice calculations. So we are eagerly waiting for their verification and studies for that. But hopefully it will be resolved fairly soon. Of course, the final thing is what if they're both be wrong, right? It's I would say highly unlikely, but we cannot exclude such a possibility. We have external evaluations, for example, some other experimental measurement, right? There is some recent interesting the muonium high fine splitting diffraction, which is from a totally different way. If you're interested, you can take a look at that. And they actually also get fairly consistent value with our experiment, although with very, very large uncertainties, right? But at least they get roughly the same range of the experiment values. And of course, there's some electron GMAS2 as well. So there's some recent development for that. And then some tau experiment, GMAS2. This is very difficult because tau is like hadronic, dominant. So this is still ongoing, I guess. So from the collider side. Okay, so this is just one of the many consistent check we have. So I don't have time to explain this, but just to say that there's many different groups, 6 independent groups to do this experiment. And then before the unblinding, they differ, and after unblinding, they all agree perfectly along this line, right? This is from our SJTU term. All right, so let me go to the outlook. So this is the current status of the experiment. We only measured wrong one. You know, there's 2, 3, 4, and 5 expected. So 25 will give to factor of 2 improvement. 4 is just finished and expect to give you 13 times more than the BNL. So it's huge improvement. And then 1.5 will give you additional that, you know, then you give you like 20. That's what our TDR go there. Okay. So if we stay the course of the same central value and just increases the statistical precision, and you will see that, sorry, yeah, just one last slide. And then you can see the significance will shrink, right, from the 3.3 into 4.5, and with 5 sigma, 1.5, you get 5 sigma. So this is not, this is not by accident, right? This is actually predicted by our TDR. That's how this experiment was designed from the beginning. So that's actually expected. All right, so this conclusion is right there. So since I had time, so I will just leave it to you. Thank you, everyone.
Thank you. Now it's time for both both talk, the last 2 about G-2. Questions? Yeah, there is one. Share.
Thanks to the 2 speakers. My question is probably more to the theory speaker.
Yes.
Okay, thanks. So 2 questions. The first is, many people think that there might be connection between the G-2 puzzle and the anomalies in B physics, namely the such as the B to K mu decay rate is significantly lower than the B to KEE. And if we use new physics to explain these anomalies, then the new physics contribution to B to K mu must contribute negatively to the total rate. Is this also the case for G2-2?
Sorry, actually the relation with the B anomaly has been discussed in the some new physics models, and for instance, the Reptokov model or vector extension model can also be discussed with the B anomalies. And
so in G-2, the new physics contribution is also negative.
Yes.
Okay, thanks. The second question is regarding the internal consistency check, which Liang just mentioned for the lattice QCD calculations. So specifically, what kind of measures you have used to check the consistency?
Actually, it's better to ask I'm not a lattice professional, so it's better to ask. I think that Luchan Jin will talk about the lattice calculation. So I think it's better to ask him. Sorry.
No problem, thanks.
Hello? Hello?
Question.
Hello?
More questions? More questions?
Yeah. I have a question to Endo-san.
Yes.
In case of R ratio approach, and for hadronic vacuum polarization, you assume unitarity and analyticity of the amplitude.
Yes.
But if the analyticity is violated somehow, then what happens?
Actually,
all people believe
yeah,
that amplitude is
because
analyticity.
that's
But
based
if-
on the S matrix analyticity.
Yeah, but
And
by some reason, the analyticity could be violated, I think.
actually, as far as we
Some
know,
pole near the cut might
actually,
exist, and every people believe analyticity. But if the analyticity is broken somehow, a little bit, then the situation could be upset.
okay,
Somehow.
okay, so the
Unitarity, we have to obey unitarity because total probability must be 1. So unitarity, we must be believe. But analyticity, we just believe. Okay.
Okay, so the question, the answer to the question is that so far we haven't discussed about the violation of the analyticity of the S matrix within the context of the mu G minus 2. And of course, if the analyticity is violated, then the R ratio approach is violated, of course. Yeah, that's true. Yeah. And but as far as we know, we haven't observed any violation of the S matrix, the analyticity of the S matrix. That's a correction. That's an answer.
So far we didn't find such a violation, but there could be a small violation of analyticity.
Actually, in my opinion, I don't believe such a violation, but if such violation has been discovered, then it's really surprising for me. Yeah.
Yes, also for me. But we could not, we can consider such a possibility. We could consider. So be careful about this possibility. That is my comment.
Next question is Tata. Tata, please.
Please. Thank you.
Yes. Hi.
Thank you.
I was curious about this pure Beano scenario that you said in the negative interference between two contributions. I didn't understand exactly the detail, but is this contribution, the corridor, the existence of the corridor, stable to corrections?
The correction to the higher order?
Yeah,
actually, it's stable about the higher order correction because we include the next order corrections. And the negative contribution means that it comes from when the mu parameter is small, there is a contribution from the right Beano-Higgs-Lino diagrams. And one of their contribution has negative sign. That is correct. That is the answer.
So it is not pure Beano. It is not pure Beano.
Actually, it's a mixture.
Okay. Because I was also wondering about that.
Sorry for my explanation.
Okay, so I have to look. Thank you.
Yes, thank you.
Yes. What question else? If not, because the time will extend a lot. So thanks all the speakers in this section again. So because now time is 32 already. So for parallel sections should be start at 10 o'clock 40.
Professor Song, maybe we will start at 10:35 in 3 minutes. Because otherwise we'll be too late for the US people.
Okay.
So we can start maybe just in 3 minutes, 10:35.
Okay.
I'm sorry about that. So we take a short break.
Remember start from you mean 35. Okay.
Thank you. Yeah.
Thanks.
Okay. Thank you.
Thanks a lot.
Yeah.
Thank you.
Okay. Close this section now.
Howie, we stay here, Howie. I am your chair.
Okay, very good. I'll stay right here in